Chapter 17.3 Earth's Temperature Controls. We're going to talk about seasonal and temperature variations. There are 4 controls of temperature. The first is latitude, the second is land and water distribution, the third is ocean currents, and the fourth is altitude or elevation. The final one on this list, cloud cover and albedo, doesn't have as much to do, so we don't consider it one of the 4 controls of temperature, but it does have an influence. The first one is latitude. On average, temperatures will decrease over land masses as we move from the equator to the poles. The lower the sun angle on shorter days over the poles contributes to that colder temperature that we experience. The land and water distribution. We know that water has a high heat capacity, which means it's slow to heat up and it's slow to cool down. Which is why when you go to the lake in May, the water's still really cold, but when you go in like, say, late August, early September, the water's still really warm. Water can distribute heat throughout its depth, so it has this ability to hold on to a lot of heat for us. The areas that are near coastlines, they will benefit from the warm water in winter, so they won't have as harsh of winter as we do here in the Midwest. They will also have cooler water in the summertime. Water helps to moderate the local climate. Sea and lake breezes influence the temperature. That's one of the reasons why we go to the lake, not just so we can get in, but because the breeze coming off the water is actually cooler than the hot, humid temperature that we would experience everywhere else. There's also lake effect snow. So as the water evaporates off the lakes, it'll create more precipitation, and since it's colder up north, like the Great Lakes region, they will have a little bit more snow than we will. Now our oceans that we have will act as these huge heat reservoirs for us. So the southern hemisphere, they will actually contain most of our heat here on Earth. The ocean currents can transport warm water near the equator towards the poles. For example, the Gulf Stream moves warm water near the Caribbean towards northern Europe. Elevation, or how high up you are, the air density will decrease with elevation, and that means there's fewer air molecules to warm by conduction. So when you go up in the mountains, it's cooler. That final one that we've talked a little bit about in the past, cloud cover and albedo. Albedo is just the percentage of light that's reflected back off of an object. So the higher the albedo, like a very white cloud or a snowbank, the whiter the object. The average planetary albedo for Earth is about 30%. Energy that's not reflected is either absorbed or it's then transmitted. Daily temperature variations, the daytime warming. Insolation, which remember is just the radiation from the sun, is going to strike the ground and it's going to heat up that surface. Those lowest layers will heat the air molecules that are in contact with the ground. Much like if you go outside on a sunny day and you touch the concrete's going to be way warmer than the air. Conduction in those lowest layers will heat those air molecules that are in contact with the ground. And because air is such a poor conductor, the conduction can't transfer all of that heat upwards. But through convection, thermals, remember those are those pockets of hot, warm bubbles of air, they will actually transport energy up and away from the surface. So when we look at daytime heating, we know that sun is at the highest at noon, but our maximum temperature here on Earth isn't reached until afternoon. That lag between maximum insolation and outgoing radiation occurs because it takes time for that heat to build up in the atmosphere and then be trapped. Kind of like when you get in your car and you start it and you turn the heat on, it takes a little bit for it to heat up. So just because you turn the heat on and you have it on full blast doesn't mean that you're going to reach the maximum temperature in your car. It'll be a few miles down the road. So our morning lows, those of you that hunt know that the lowest temperature of the day is just after daybreak. So sunrise, not just before, but actually right after the sun comes up, that's when our temperatures will bottom out. The daytime highs occur in late afternoon. So on a calm sunny day, the air near the surface of the Earth can be much warmer than the air a few meters above it. So there's a temperature difference between right here on the ground and if you get up, say you climb a tree. There is a big temperature difference just between your feet and your head. And if you don't believe me, stand up on your chair and feel the difference between the top of the room and down on the ground. On a windy day, though, mechanical mixing caused by that wind stirs up those lowest few inches, and it will actually distribute the heat upwards. So a lot of times a windy day will feel cooler because it's moving the heat around. The temperature difference is minimal in those lowest few feet down here. Then at nighttime, when the sun goes down, the ground will actually radiate energy out to space. So the ground has been absorbing all of that energy throughout the day. And then when the sun goes down, that heat, remember the law of thermodynamics, it's going to transfer from warm to cold. So that radiational cooling of the earth occurs. So the ground is going to give off heat. The conduction of heat from the lowest few inches of air into the ground occurs, and then it works its way out to space. That air closest to the ground loses heat rapidly, forming a nocturnal radiation inversion. Remember, warm air rises and cold air sinks. So the nocturnal radiation inversion, in order to get a good one of these, we have to have a calm night, so no wind, no clouds, low moisture content, and we have to have a long night. So on a calm night, we will have a better temperature inversion, and it'll actually get colder. On a windy night, though, we have a poor temperature inversion, and we end up with warmer temperatures overnight. Those warmer temperatures overnight will lead into the next day and the amount of energy that's in the system. Well, there we go. Low temperatures, those occur around sunrise. The outgoing energy will actually exceed incoming energy. The high temperatures come in the late afternoon and the early evening. The incoming energy will exceed the outgoing energy. So in a perfect day, we will have high amounts of insolation, the sun will shine, the ground will pick up heat, there will be evaporation, and then the sun goes down and things start to cool down. It'll continue to cool down until the sun comes up, and we'll bottom out our temperatures and we'll start the whole process over again. Now when we add clouds into the mix, those cloudy skies, when they happen at nighttime, will actually act as a blanket. So as that radiation from the ground is trying to escape, if it's a cloudy night, it will actually keep all of that heat trapped towards the surface, and so we end up with warmer nights. If we have clear skies at night, it allows for that heat to release. It lets that radiation escape, and so we will end up with a cooler overnight temperature. So warm during the day, cool at night. This is a typical day. But when we throw clouds in during the day, those clouds will act like that blanket, and they'll trap that radiational energy coming off the ground that it's been absorbing, and it bounces back, and so it will trap it right here in this cycle. The incoming radiation only happens during the daytime, so we're not worried about it at night. If there's clouds during the day, though, that incoming radiation is blocked, and so we'll end up with a cooler day, which you guys know this. If it's a cloudy day, it's usually cooler than if it's a sunny day. When we talk about air temperature data, one of the things that we'll discuss is diurnal temperature range, and that's the temperature difference between the minimum and maximum temperatures in one day. You're going to have a larger diurnal temperature range on a sunny day than on a cloudy one, because remember, if it's cloudy, you're not going to fluctuate temperatures much. You're going to have a larger temperature range on a dry day than on a humid one, because remember, moisture in the air is just like moisture in a lake or an ocean. It's going to have the ability to hold on to heat better. And it's also going to be larger over man-made surfaces like pavement or concrete, which is why cities often have higher temperatures than we do out here in rural areas. The other thing that we're going to talk about is a mean daily temperature, which is just the average of the highest and lowest days temperatures. So when you look at your phone and you look on your app, you're looking at the mean daily temperature. Most of the time you're not going to see a temperature range unless it's something significant, and the meteorologists are like, wow, we've got quite a temperature change today. They're talking about the temperature range. So if we start the day off and it's 30 degrees and we end the day at 70, that diurnal temperature range would be 40 degrees difference. That means that it was probably a sunny day. it was probably a dry day, and it was probably a temperature taken over, I don't know, probably a city. The mean daily temperature, when we talk about, oh, yesterday it got up to 70. It may have got up to places 71, 72, but the average high would have been 70, and then the lowest was whatever the daily low was. So the annual range of temperature is a little bit different. We're not talking about the days, we're talking about the year. So the difference between the average temperature of the warmest and coldest month in one location would be the annual range of temperature. The annual average temperature is the average of 12 monthly temperatures. Let's see if we can get this to show up. There we go. So in January here, the average monthly temperature was 28. February was 34, and so forth, and we go all the way through. Traditionally here in Missouri, the coldest month of the year is January, and the warmest month is July. And we can see here this was a Columbia average monthly temperature. If you were going to do the yearly or the average annually temperature, if you were trying to calculate that, you would add up all 12 of those monthly averages, divide them by 12. So it's just like math class. So when we talk about using temperature data, one of the things that's discussed is heating degree days. This assumes that people will use their heater when the average daily temperature drops below 65. So if it gets down to, if the temperature outside is 64 degrees, the general assumption is that people are going to turn a furnace on. And this is used by electric companies to estimate usage. In order to get this, you're going to use the same basic formula here. You're going to subtract the mean daily temperature from 65. So if the maximum temperature of the day was 62 and the minimum was 46, you're going to come up with the daily average temperature, which is taking the maximum temperature plus the minimum and then divide by 2. So your average daily temperature for that day was 54 degrees, which is much cooler than that 65, which is that magic number. If we get much below 65, most people are uncomfortable and they start complaining about being cold. You guys in my classroom, if it gets below 67, that's when you start complaining. So in order to calculate the heating degree days, you would take 65, which remembers that magic number. That's where people are the most comfortable. And you're going to subtract the daily average temperature, which was 54 that we came up with. And that's going to give you 11. And so that's just a rating that the electric companies are going to use to estimate usage. They don't actually come out to your house and read how much electricity you use every day. They have to estimate the usage, and they do that by using the temperatures that are provided. Now a cooling degree day works in the opposite direction. This assumes that if it gets much higher than 65, people are going to be uncomfortable and turn their air on. So this again is used by electric companies to estimate usage, and we're going to work with the same basic concept, but we're just going to go in the other direction. So you're going to take the minimum and maximum daily temperatures, add them together, divide by 2 to get the daily average temperature. And then you're going to subtract 65 from that, and that'll tell you the cooling degree day. So a 12 cooling degree day. So on a day like that, if it's 77 degrees outside, you're probably going to have the air maybe on, but it's not going to run consistently. So you're not going to be using a lot of electricity running your air conditioner on a day like that. If it was a really, really hot day, and it was like, say, a 30 cooling degree day, you're going to be using the electricity a lot more because it's going to have to work harder to cool the house down. Now a growing degree day works with the same basic premise. Farmers are going to use this for planting and harvesting dates. You subtract the plant's base temperature from the average daily temperature. So for corn, in order for corn to germinate and grow, it has to be 50 degrees. So we would assume that for every 50 degrees, we're going to have a growing day. If it's below 50 degrees, those plants aren't going to grow. Soybeans have a growing temperature of 40 degrees. So our example here, if let's say it was a really sunny day in May, and the maximum temperature got up to 84 degrees Fahrenheit, and the minimum only dropped down to 70. It's not a very big gap. The average daily temperature, remember we take the minimum plus the maximum, divide by 2, it's going to give us 77 degrees. And then we're going to subtract, because we're trying to do corn, you subtract 50 from it. Okay? That's going to give you 27 for a growing degree day number. Now, all of those numbers would add up every single day, and corn is typically harvested after you reach 2200 growing degree days. So the warmer it is, the more you're going to get out of those growing degree days. That's how that works. So air temperature in humans, so how does it affect us? There's an exchange of heat between the body and the environment, and that determines how comfortable we really are. The wind chill index that we talk about a lot in the wintertime is based on the temperature and the wind speed 5 foot off the ground. The higher the wind is blowing, so the wind speed, if it accelerates, it's going to blow the heat off of your skin much faster, and thereby making you colder faster, which is why we're concerned, especially about little kids being out when it's really, really cold and the wind starts blowing, because it puts you at greater risk for frostbite. The heat index is something we talk a lot about in the summertime, and this is based on temperature and humidity. A high humidity prevents perspiration from evaporating and cooling off your body. So if it's very, very humid, so think about around here in August, when you step outside and you just feel like you're coated in sweat already, that's a high humidity. And that's going to keep you from sweating, which is how your body cools itself off. So weather and climate, there is a difference. Hopefully you know there's a difference here. The difference between weather and climate is a measure of time. Weather is what conditions of the atmosphere are over a short period of time, but climate is how the atmosphere behaves over long periods of time. So when we talk about climate change, we're talking about changes in long-term averages of daily weather. Here we can kind of see the different climates, like a tropical grassland versus a tropical rainforest, versus hot deserts, polar tundras. In addition to long-term climate change, there's shorter climate change variations. These so-called climate variabilities can be represented by periodic or intermittent changes related to El Niño, La Niña. They can also be attributed to volcanic eruptions and other changes in the Earth's system. So what would the world look like if we raised the average temperatures just 4 degrees Celsius? If we were to look at this model. Here we can see Greenland's ice sheet. You know Greenland's covered in ice, and Iceland's covered in green. So Greenland's ice sheet would be melting very rapidly. All of Canada and Alaska, all of this would be green. There would be no sea ice, and so the valuable shipping route, it would be open all year long, and that would provide transportation links between habitable zones in Canada and Russia. Because remember, it's just a very short on the globe. It's a very short passage from this point to this point. Now, Canada would have more reliable precipitation. There would be warmer temperatures. The Midwest, however, we would be more like northern Africa. It would actually be more desert-like conditions here. And then parts of the southwest U.S., they would be less likely to be habitable, and so a lot of people would have to move out of there. We would see western Antarctica unrecognizable. It would no longer be covered in ice and snow. Australia, parts of it would become greener, but parts of it would also become inhabitable. So what weather really means, it's basically the way the atmosphere is behaving, mainly with respect to the effects on life and human activities. The difference between weather and climate is that weather consists of short-term, like minutes to months, changes in the atmosphere. Most people think of weather in terms of temperature, humidity, precipitation, how bright it is outside, the wind pressure, the high and lows. In most places, weather can change from minute to minute, hour to hour, day to day, and season to season. In lots of places here in the Midwest especially, because we don't have lots of water around us, we have a little more drastic changes. Something about the geography of how flat Kansas is, and how storm systems can ramp up over the Rockies, and when they come down and they hit the high plains of Colorado, and then they come scooting across Kansas, by the time they hit the Missouri River, by the Kansas-Missouri line, some of those storms can become very violent, and that's what leads us to why we're called Tornado Alley. So just the setup, the geography, it allows for those serious storms to build. Climate, however, is the average of weather over time and space. Kind of like we know that every February it's probably going to be snowy and we know it's going to be cold. The best way to remember the difference is that climate is what you expect, like a very hot summer, and weather is what you get, like a hot day with a pop-up thunderstorm, like, oh, this is an unseasonably warm day in November. The other way to remember it is climate is like your personality, and weather is your mood. So, in short, climate's that description of the long-term patterns of weather in an area. Some scientists define climate as the average weather taken over 30 years. It's really just the average pattern of weather for a particular region. When scientists talk about climate, they're looking at averages of the precipitation, temperature, humidity, sunshine, all sorts of things, different phenomena such as fog, frost, hailstorms, other things. So knowing that there's a difference between weather and climate is important when we discuss it so that everyone's on the same page.